Hello everyone. Hope you guys have enjoyed previous lecture for finding minimum spanning tree using Kruskal algorithm. In this lecture, we're gonna be discussing about Prim's algorithm for finding minimum spanning tree. Um, Prim's algorithm is very similar to what we did in the very first lecture of a spanning tree, um, where we discussed generic spanning tree algorithm. And we discussed a digital circuit example and converted it into a graph, and we're going to be using the same graph example in this lecture. The basic idea behind Prim's algorithm is that it starts from a vertex. Kruskal algorithm starts from edge, Prim's algorithm starts from vertex. That's the key difference. Now it takes an arbitrary vertex and keeps on spanning the tree until it uh, explores all the vertices in the original graph, right? So let's say what this algorithm says. There are some initialization steps because uh, this algorithm make use of min heap property or uh, say min priority queue. So we got to um, initialize the data structure for some things. Okay, for example, the key for all vertices, we assign it to a very high value or infinity, and parent of each node is null. Okay, why we are using the parent field? Because that will give us the tree. Okay, which is the parent of which node? So that way we're going to construct the minimum spanning tree. Okay, line number 4 says that okay, select an arbitrary vertex and make its key to 0. Step number 5 is initializing a queue. Now that's the important aspect of this algorithm. You can use the queue in two different kinds of implementation. You may use uh, binary heap, uh, or so binary heap, which uses the min heap property, and the another implementation could be Fibonacci or Fibonacci heap. Okay. Now Fibonacci heap that is also using the min heap property. Depending upon your implementation, the time complexity of this algorithm would be different because we're going to be searching and extracting from this queue, okay, as the algorithm unfolds further. So as you can see, line number 7, we have extract operation, extract min operation on the queue, and at line number 9, we are trying to find that whether a node or a vertex belongs to the queue, means we are doing a searching operation. So two major operations, extract min and searching operations, we're going to be doing in this algorithm. So it's important which data structure we do choose. Binary heaps are simpler to implement compared to Fibonacci heaps. We discussed both kinds of data structure in previous lectures. If you are not familiar with that, I would recommend you to go and watch previous lectures. All right. So, so what is the essential idea is that we put all the vertices from the original graph in a queue. Okay, and then we just extract the minimum key value vertex from the queue and find all the adjacent vertices uh, or all the adjacent vertices of that minimum key value vertex. And we execute line number 9 to 11, which makes sure that we select the the minimum edge or minimum weight edge uh, while we progress through the graph, or we span through the graph. Okay, and that also will make sure that we won't have any cycle in the tree. Okay, and then in the end, when the uh, algorithm exits the tree, okay, or set of edges which will be in our minimum spanning tree can be given by this expression number 3. All right. So the queue, implementation of queue is very important. The overall time complexity of this algorithm will depend on the implementation of this queue data structure. So now let's see how, on our example, how this algorithm unfolds. Good. So initially, we initialize the graph, put all nodes a key value infinity or very high value, and we arbitrarily select a root node. Let's say A is the root, and we change its key value to 0, and we put all the vertices in our queue, right? So if we select A, what are the adjacent vertices from A? That is B, E, and D. Remember, the D value initializes, we initialized with infinity. Okay, so if we select D, okay, now we are at line number 9, that D belongs to Q, and the edge between A and D has a weight 2, which is less than infinity. So we satisfied the line number 9 condition at line number 9, and we're going to execute the steps 10 and 11, that the parent of D is A, and the key of D is 2, which is the weight on the edge between A to D. Simple. Now let's say if we select next adjacent vertex from A is E, and we're going to do the same operation what we did for uh, D. We're going to take the same steps. So we are again back here at line number 9. E belongs to Q. Yes, E belongs to Q. And weight on A and E3 is less than infinity. Okay. So we satisfied both conditions. We're going to execute line number 10 and 11. So how it will look like? We have updated the key value of E to 3, and how it does it, we updated its parent, which is A, and in a tree form it will look like this. Now another adjacent vertex to A is B, okay, and we're going to execute line number 9. B belongs to Q, true, and weight on edge A to B is 4, which is less than the key value of B, which is infinity, and true. So we're going to again execute line number 10 and 11, and how it will look like? Very simple. We updated the key value of B, which is 4. Parent of B is A, right? So we finished the for loop at line number 8. Now we are again at line number 7 because our queue is not empty, okay, and we extract another element. Remember, this K is gone now. Remember, this A is gone now because we have extracted already from the queue. Okay, so next element from this queue which has minimum key value, which one would be? So we have left D, E, B, F, D, C, G. Okay, so D would be our next minimum key value node. Okay, so we select D, and now we find the adjacent vertex, because for each vertex which is adjacent to D, we execute line number 9 to 11, and at the line number um, 9 we have the condition, two conditions to fulfill. So let's see what are the adjacent vertex of D. One is A and one is E. Now if we select A, okay, so the condition at line number 9 says whether A belongs to Q. Now A is not in the Q now anymore, A is gone, so we don't satisfy this condition at line number 9, and we exit out of this condition at line number 9. We don't execute line number 10 and 11. Now we take another adjacent vertex, which is E. Okay, now at E, if we take E adjacent vertex, what's going to happen? E belongs to Q, true, so one condition at line number 9 is true, but the weight between D and E is 5, which is not less than V dot key. So 5 is bigger than the key value of E is 3. So we again do not execute line number 10 and 11 because we do not satisfy the condition at line number 9. Okay, good. So now next we find, which is the we again are line number 7, and we execute the same operation, extract min, and next minimum key value vertex is E. Okay, and now adjacent to E we have A, we have B, we have F. So if we take A, same thing, A doesn't exist in our queue, so we will not satisfy the condition at line number 9, and we will not execute 10 and 11. Okay, now if we select next adjacent vertex F, good. So what's going to happen? Earlier the value of F was infinity, and F exists in the queue, so everything is good. We end up making changes for the vertex F. As you can see here, we updated its key value and we updated its parent. F's parent is E. Now next adjacent vertex to E is B, and we got to take decision on B. Okay, so B exists in Q, good. So we are good at first condition. Now the weight on edge between B and E is 8, and 8 is bigger than 4. So we do not satisfy the second condition at line number 9, and we don't execute line number 10 and 11. All right. Now we again finish the loop at 8 and went back to the line number 7, extract min. So now B is left, which has the minimum key value, and B has the minimum key value. We select the B, and adjacent vertex to B are F and G. Okay, and E. Now E is already done. We have no more E in our queue, so we will not execute the line number 9, 10 and 11. Okay, another adjacent vertex to B is F and G. So let's see, we take G this time. So G, earlier value of the key was infinity, and G is still in the queue, so we do the same operation. We update its key value, we update its parent of G is B. Okay, now we see another adjacent vertex to B is F. Okay, now here is the tricky thing. Now see, between B and F that edge that has weight 3, which is less than 8. Okay, so we are satisfying one condition at line number 9, and f is also exist in the queue. So we are satisfying both conditions at line number 9. So we're gonna end up executing line number 10 and 11 for the vertex f. So how it's gonna look like? Well, simply that earlier parent of f was e, that parent will be now b. So we made changes accordingly. New parent of f is b, and we change the key value of b to 3, which is the weight on the edge between b and f. Okay, now we have no more adjacent vertex left from the b. Good. So b is already gone from this list. We are again went back to the line number 7. We're going to execute the extract min operation. Means that we're going to find the minimum key value node from this queue. Okay, so we find that okay, now the minimum key out of G, F, and C, G, F, and C have F and G have value 3. So let's select the F. Okay, so now adjacent to the F, what vertices we have? We have B and we have E. Only 2 vertices adjacent to F. Now if we take B, then we do not satisfy the condition at line number 9 because B is no more in Q. Okay, now we are again back to line number 9 for the adjacent vertex E, and E is also no more in the Q. So we are done with the line number 9 and we don't execute 10 and 11. Okay, and now we are again back to extract min Q. Now we have left G and C, so next would be G. So let's select G. Okay, G. So adjacent to G we have only one vertex, which is C, and we made all the changes. We execute line number 10 and 11, and the key value of the C we change it, and we change the parent of the C, which is G. Okay, so good. We now finally the C is left in our queue. So now let's see C. We have only one adjacent vertex to C, which is G, and G is no more in the queue. So we don't execute 10 and 11 for this, and our queue is finally empty. So as you can see here that how this algorithm unfolds for finding minimum spanning tree. Okay, now let's try to understand the complexity of this algorithm. It's the extract min operation. Okay, that's gonna take v log v time. Okay, now we are assuming here, let's say, binary heap or say priority queue. Okay, priority queue. And from line number 9 to 11, we're gonna execute in order of E, right? So if we see from line number 6 to 11, okay, the total time, how much is gonna take? Simply v log v plus E log v. Okay, and need to mention that these initialization steps are all done in O1 time. Okay, constant time. And now you can solve this equation O of v log v plus E log v, that turns out to be O of E log v. Okay, so that is the complexity, asymptotic time complexity of Prim's algorithm. Okay, if we are using binary heap data structure for maintaining the queue, and which is same as Kruskal's algorithm. However, if we decide to use Fibonacci heap data structure for implementing this queue. Okay, we can get a better asymptotic values for time complexity, and which would be e plus v log b. Okay, Fibo means Fibonacci heap structure, that time complexity you can get. So see how this algorithm, Prim's algorithm, works for finding minimum spanning tree of it from a graph. All right. So thank you very much, guys, for liking and subscribing Lee Professor YouTube channel. We appreciate your support, feedback, and any questions you may have. You can send us an email, or if you like to have private consultation, private tutoring, or private help, you can send us an email, and we can set up a time for online consultation. And thank you once again. Those who have not subscribed, please do subscribe, and have a wonderful day.